Now that we've talked about chords and finding their measurements within a circle when they cross one another, we're going to go ahead and talk about chords and what they do with the arcs in a circle and how they kind of work together. So we're going to identify minor and major arcs, use properties of a semicircle, and then also inscribed polygons, which we'll talk about as well. So 4 different terms you have to know. First is minor arc, any arc between 0 degrees and 180 degrees. So it can't be 0 because it would be non-existent, and it can't be 180 because if it's 180, it's a semicircle. And a semicircle is half of a circle, and a semicircle is also always made up of the diameter, which may be a good thing to kind of write down there. Then we have major arc, and a major arc would be any arc between 180 and 360. So it can't be 180 because then that would be a semicircle, and it can't be 360 because then it would be a circle, so it's in between the two. Then we have inscribed polygon, and an inscribed polygon is any polygon whose vertices are on the circle. So when you have a circle, each vertex needs to be on it, which we're going to see here in a little bit. Our first theorem that we're going to use and work with is 2 minor arcs are congruent if and only if, and remember that's what this thing is right here, that's the if and only if statement, their chords are congruent. If we look at this picture, and I tell you that RS is congruent to TV, and now you see how that's a segment mark over the top? This right here is how you indicate arcs. And what we're saying then is that RS, the arc, is congruent to TV, the arc, in terms of degree measurement, in terms of length if we were to straighten it out. So from here all the way to here is going to be exactly the same as from here all the way to here. And you'll notice also that it's the same 2 letters, just with that different marking on top, which is really important that you know we're talking about the arc and not the talking about arc RS and not the 2 other ones that are formed. So here's our first example, and we're going to actually find the measure of arc BC right here. Well, you'll notice that these 2 chords, so a chord because it has its 2 endpoints on the circle, they are marked as congruent, which would then mean that these 2 arcs here are congruent. So arc BD is congruent to arc BC because BD, segment BD, is congruent to segment BC. So those are chords, so that makes the arcs congruent. So we go ahead and take our 2 degree measurements and set them equal to one another. I don't know why I wrote 4, sorry. So 2x plus 48. Subtract 2x from both sides of your equation to give you x plus 11 equals 48. And then subtract 11 from both sides of your equation to get x equals 37. Now remember to always go back and double check what it's asking you for, and in this case it's not asking for x, it's asking for the arc BC, so we need to plug that in. So I'm going to take this 37 here, and I'm going to plug it in right up there. So 2 times 37 plus 48. So BC, arc BC, or the measure of arc BC is equal to 122 degrees. Second example using the same kind of logic. So here's ED, this chord has an endpoint here and here. And then DC is another chord, and they are marked as congruent, which then makes these 2 arcs congruent. So again, because CD is congruent to DE, then that implies that arc CD is going to be congruent to arc, oh, I can't fit that in there. The thing won't let me write arc DE. Sorry, that should be up here. I just can't write it up there. So since they're congruent, we set them equal to each other. So 4x equals x plus 78. Why do I keep running to write 4s? Subtract x from both sides of your equation to get 3x equals 78, and then divide by 3, and you end up with x equals 26. Now, come back here. If BE is a diameter, well, why would that be important for this problem, for BD to be a diameter? Well, what that means then is we have a total from here all the way to here is a total of 180 degrees, and from here all the way to here is also 180 degrees. So what that means is that our arcs BC plus CD together make 180. So we can find the measure of CD by plugging 26 in here. So we get BC plus, and then 26 plus 78 is a total of 104. So 104 equals 180, which would mean that arc BC would have to be 76 degrees. So again, that was taking this 26 and plugging it in right there. So that part is actually really important. If that wasn't a diameter, we wouldn't be able to use that idea to solve this problem. Third example, we've got a hexagon and it's inscribed in circle K, so circle K. And the hexagon is regular. Well, remember, regular means all congruent angles and all congruent sides. So if all the sides are the same, then that means we have 6 congruent chords. So if we have 6 congruent chords, there's always 360 degrees in a circle. Okay, always. So if there's 360 degrees total, and we know that all these chords are the same, then what happens is we form all congruent arcs as well. And if they all have to be the same, all you're going to do is take your 360 and divide it by divide it by 6, because there's 6 different chords, all with the same degree measurement. So 360 divided by 6, which leaves you with 60 degrees for each arc individually. And this will only work with regular polygons, very important. The next theorem that we have 2 more that kind of work together quite often. If you have a diameter or a radius, either one, and it's perpendicular to a chord, so meaning it makes that right angle right there, then it bisects the chord and its arc. So this is your chord that is being bisected right here, and then this would be your arc that is being bisected. So I'm going to go ahead and add a letter in here. Let's use Q. So that way we can write down that RQ is congruent to QN, and arc RP, so put the arc symbol, is going to be congruent to arc PN. Okay, so those are equal as well. And then we have obviously our diameter right here. We don't really know what this segment is, but we can work with some stuff to find that out later. So here's another one, kind of the same idea. So you see that this radius here is perpendicular to our chord, but if you have 2 totally different chords that are the same distance from the center, right here and right here, then these the 2 chords are going to be congruent as well. And because AB, so let's go ahead and write this, AB is congruent to CD, right? So those are congruent to one another because these are equidistant from the center. So QP is congruent to RP. And so that also would make these, all 4 of these would be the same as well. So it kind of looks a little bit confusing, but it makes it easy because you're either cutting things in half or maybe doubling them, but it makes it pretty simple to work with. So here are the first 3 examples using those last 2 theorems that we talked about. So I'm going to go ahead and label the picture. The radius is 13. So the radius is from here to here, right? But to kind of keep it a little bit less, messy, I'm going to draw in my own radius, and I'm actually just going to connect it here to R. So I'm going to draw my little radius right here, and I'm going to label it as 13. Because remember, no matter where you put your radius, it's going to be the same from the center to the side, or to the circle. All right, now RS is 24. Well, this right angle right here tells us right off the bat that this gets cut in half. So if this whole thing is 24, then each little piece must be 12. It has to be. All right, and then that's all that we have for now. So let's go ahead and look at our information. What do we need? Well, we're looking for RT. We already got it. RS was 24. RT is half of that. It's 12. And again, that's because of your right angle. Now PT we don't have, it's right here. But if you notice, I'm gonna go ahead and pull this out real quick. So here's RT, here's this little section from T to P, and then this gets connected right here. Here's a right angle. We have a right triangle where 13 is our hypotenuse and 12 is the side that we have. This is what we want. So a squared plus b squared equals c squared. So this is across from your right angle, so this one is your hypotenuse, making it your c. Now it is a Pythagorean triple, so some of you may already know what this length is here, but if not, you take a squared plus 12 squared equals 13 squared. So a squared plus 144 equals 169. Subtract 144 from both sides to get a squared is 25. Take the square root of both sides, and a is 5. And a represents our little question mark here, so PT is 5. Now we're looking for TQ. Well, if you look at this whole segment, QP is an entire radius, right? And we know that the radius is 13. So if the radius is 13, so we've got Q, T, and then from T to P. We know that this is 5, and we know that this whole thing has to be 13, which automatically makes this 8, because 8 plus 5 is a total of 13. So there's your TQ. All right, last three using the same kind of concept. So this time we have a diameter, it's 12, but what I'm going to do just for terms of labeling it, I'm only going to use the radius from A to B, and I'm just going to label that as 6, because we know that the radius is half of the diameter. Now CD is 8. This right angle right here, and the fact that this is a diameter, means this gets cut in half. So instead of labeling each one, or the whole thing is 8, I'm just going to label each one as 4. Then measure of arc CD. So from here all the way around to there is 90 degrees. And actually I have to shift this over because my pen won't write over that far. So I'll shift it back in a minute. So from C all the way to D is 90 degrees total. Well, what we know is that if these are congruent here, so this arc, and this is being bisected, it also bisects this arc over here, making this a 45-degree arc, as well as this being a 45-degree arc. Okay, so now I can shift everything back to where it was. There we go. And find the measure of arc DE. Already did it. It's 45 degrees. Easy peasy. FD. Already did it. It's 4. AF. Now that we don't have. But if you're looking at the picture from A to F, there's a right angle. From F to D, we know that one because we already labeled it as 4. This is your right angle. From A to D is your radius, right? And we already know that our radius is 6. So we again can do our Pythagorean theorem. That's your hypotenuse. So a squared plus b squared equals c squared. 4 squared plus b squared equals 6 squared. So 16 plus b squared equals 36. Subtract 16 from both sides of your equation to get b squared equals 20. Take the square root and you get b is the square root of 20. Now you can leave it as the square root of 20. You can do the decimal form of it, which is which this means about 4.5. You could do that as well. So now that we know that that little section right there is 4.5, we'll go ahead and write that in. So it's about 4.5, right? Okay, well, FE, right, or not FE, I'm sorry, A to F, because we're looking for FE. From A to F is a total of 6 because AE is a radius, right? So if AE is a radius, which I can't get on there, dang it, try this again. There we go. AE is a radius. Well, AE is made up of AF plus FE, right? And we know that the radius has to be 6. So if AE is 4.5, we need to know what would we add to that in order to get 6, and it comes out to about 1.5. And so that would be your answer for FE. So we've got Pythagorean theorem, properties of circles. It's a lot, but it all kind of works really nicely together. So just make sure you have everything written down and come in with any questions.